Welcome to the normal distribution. Until now, you have counted discrete outcomes, like heads on a coin. But real life is continuous. We measure things, like human heights, the lifespan of components, or exam scores. This unit is about finding the probability of continuous data falling within a range by calculating areas under a perfectly symmetrical bell curve. It is arguably the most important distribution in all of statistics. We begin with the purely theoretical shape of the curve. This is the normal curve. It is defined by just two parameters, the mean, mu, which sets the center, and the variance, sigma squared, which dictates the spread. Because the data is continuous, the probability of any exact single value is 0. Instead, the total area under the curve is exactly 1, and we find probabilities by looking at intervals. Notice the perfect symmetry. This is a powerful tool you will use to deduce probabilities without complex maths. Every real-world scenario has a different mean and variance. To avoid complex calculus for every single question, we map everything to one universal baseline, the standard normal distribution, called Z. It has a mean of 0 and a variance of 1. You will learn to use the Cambridge statistical tables to instantly look up probabilities for this standard curve. The tables only show positive Z values, so you will master using that symmetry to handle negative values effortlessly. How do we get to that baseline? We standardize. You will use this formula to convert any raw score, X, into a standard Z-score. You simply subtract the population mean, mu, and divide by the standard deviation, sigma. A huge trap here is dividing by the variance instead of the standard deviation. Always double-check your denominator. Finding a forward probability is just the warm-up. The real exam heavy lifting is working backwards. You will be given a final area, and you will have to use the tables in reverse, set up algebraic equations, and solve for an unknown mean or standard deviation. For top marks, you will even standardize twice and solve simultaneous equations to find both at once. Finally, we bring it all together. When a binomial distribution has an unmanageably large number of trials, calculating it directly becomes computationally overwhelming. You will learn how to approximate it using the normal curve, but bridging the gap between discrete counts and continuous measurements requires a crucial adjustment called a continuity correction. Getting this right is often the difference between an A star and a B. This unit is highly sequential. Master the standard tables and standardization first, and the complex algebra will fall into place. Always sketch your curve, watch your standard deviations, and let's get started.